Hi, everyone, and welcome. We're going to talk briefly around issues dealing with high noise environments and the challenges associated with keeping your voice data clean in those environments. My name is Ken Sutton. I am co-founder and CEO at yobe Inc. Here at yobe, we create intelligent edge-based software that can track and extract voice signals in high noise environments. We do this while preserving the linguistic and biological markers any platform needs for accurate voice analysis. And so, what we found as voice platforms start to move into more commercial and enterprise type environments, these are the type of environments where thresholds for errors are extremely low. However, the environmental complexities are much more dynamic. The risk for you or your organizations getting this solution wrong in reference to your client's brand is extremely high. So we've seen scenarios where a lot of our ASR partners, spend time and resources to acquire the proper speech data set to train their core algorithms on. And then they find themselves in situations where they have to be a little more robust to the noise in whatever particular environment that their solution is going to be deployed. And so, they'll go back to their training, their data set. They'll add artificial noise to the training data to make it a little more robust to the issues associated with the environment. However, in many situations, let's say like in retail environments, automotive settings, restaurants, public venues, etc., these are environments where the noise is dynamic in nature, and it's very challenging to model your way out of these situations. So you traditionally would look for an audio front-end partner, someone that can come in and effectively mitigate the noise issues. However, many solutions are not fully adaptive to the changing environments, especially with those dynamic environments. And more importantly, a lot of solutions end up creating unwanted artifacts that corrupt your input data. So our solution has been to take more of an intelligent listening approach. And we start with three building blocks of our core technology. One is artificial intelligence. We use unsupervised learning to adapt to those ever-changing auditory environments. And we basically use inferencing AI to do that. And then we layer a section of biometric tracking. Our solution is always looking for the voice biometrics in the high noise environments. And that's what we use to differentiate voices from other voices, as well as voices from noise. And then the last layer is some signal processing IP that we have that basically does not introduce the unwanted artifacts that you traditionally find when you aggressively signal process something that is in a noisy environment. And so when we blend those three building blocks together, we get an interesting conversational focused audio front end. We call it an intelligent conversation audio front end, or CAFE for short. And the real premise around CAFE was really to focus on preserving the linguistic and the biological markers that you need to extract in low SNR type environments. And, our methodology is different than most. A lot of it is by design, our design approach. So we start by using inferencing artificial intelligence. We don't use modeling or large data sets. We are basically focusing on a biometric type approach. We're looking for the voice biometric in the signal. We are environmentally adaptive. So as the scene changes, our solution changes along with it. We're extremely modular, so we can fit into any package, in any solution, in any type of environment from a need standpoint. We are highly computationally efficient. We are in the microcontroller space. We can go down to the core type of microcontrollers if you're talking in the ARM vernacular. And we are using, as I said earlier, unsupervised learning, which allows us to be highly adaptive. And the net benefit of having a solution that can be on the edge, that can be adaptive, is the benefits to ASR platforms or any type of conversational platform that needs to have accurate speech input for its data set. And this is an example of something we did in an automotive type environment. And you see here, we're using Google's ASR as the engine. And right around the 0 dB SNR range, this is when your signal of your voice or the voice of interest and the noise are at equal levels. This is where traditionally most ASR engines start to have increased errors or start to break down. And you see here from this example, with the yobe solution running as the conversational front end, we are able to get, in this scenario, 17 dB bounce to improvement. So we're going into the negative 20 dB SNR range and still giving the same accuracy as if we were in a 0 dB range. Now, for a lot of our customers, they're going into areas where they are functionally living in a negative dB SNR environment, that -5 to -20 dB SNR range. And a lot of scenarios fit that criterion. You have in-cabin situations if you're working in a car or a truck and you want to use voice commands. We work with a lot of first responder groups where, of course, the scene is pretty noisy when the first responders are replying to jobs and working in environments that are traditionally outdoors in nature. Industrial settings where there's a lot of machinery, home appliances. This is a very unique scenario where you want to put voice control into a washing machine or something that is generating its own noise. However, the purpose of voice would be for you to have a far field voice talking to the appliance that you want to interact with. So the near field noise creates a -20 dB SNR environment because of its proximity to the actual microphone in question, as well as you working in areas like public venues, whether it's a kiosk in a mall or in any type of public venue where you have a lot of ambient noise, as well as you might have wind if you're in an outdoor environment like an amusement park. And you also have people talking. You have other conversations going on, and the challenge of extracting the voice of interest from that dynamic environment can be challenging. And so I'll do a quick demo here, and hopefully you can hear the audio. This was pre-recorded, and the scene that we're using here is a automotive scene. And what will happen is this is our solution running on a edge device. It's I believe it's a Motorola Android phone, a pretty common processor. And it's on the edge, so it's not connected, so there's no internet connectivity. And what we'll do is we'll just give a demonstration of our solution working in real time on an edge device.
Show me directions to the nearest CVS. What time is my appointment tomorrow?
So hopefully you were able to hear the difference, long lines between the before and after. And if you want to see some of those demos live, we have a few representations of similar type of demos on our website. But the gist of that demonstration was really to show in those high noise environments, the accuracy and the errors rather that are generated when there's a high noise environment. And so we've done enough studies with third-party groups to basically benchmark our solution in front of your traditional or I would say incumbent type of ASR engines. And so this chart here is in a -10 dB SNR environment. And this particular, I guess, experiment was done with Amazon, Google, Microsoft, and IBM Watson. And what these bars represent are in a -10 dB SNR environment, the errors for each one of those engines. And they were, basis points within errors of each other, but they were all in a high 98 plus percentile of errors. So basically, many of them were, at least two of them in this example, had 0 words recognized. And so they, in the 99 to 100% word error rate zone. And with our solution, because we are agnostic, we are not tuned to any ASR engine, it's just a intelligent front end. We were able to decrease the errors tremendously across these platforms. And you see the individual decrease in errors for each platform. For IBM Watson, we had a 90% decrease at a 10 dBs in our environment. For Google, it was a 99% decrease. For Microsoft, a 96% decrease. And for IBM Watson, it lagged a little behind the others at an 81% decrease in errors. So we're enabling these solutions to work in these noisy environments as just a simple plug and play software audio front end. To close, high level, our solution is 100% on the edge. We don't use any connectivity. All of our packages sit on device. We don't use training modeling or training data for modeling. There's no modeling necessary. So it allows our customers to use their traditional data set without any real augmentation. The AI in our solution adapts dynamically to the changing auditory environment. We are 100% dynamic in nature. We don't need any prior information about the audio scene. We don't need reference signals. We are doing all of our computationals lift, or all of our computations rather, in real time on the edge on the device. Our unique biometric focus methodology allows us to separate and track voice of interest, not just from noise, but also from other voices. We do have some demos on our site that are more in reference to our biometric extraction. We do have a biometric identification solution for those who want to speak or identify. And then lastly, large data point for us is that even in noisy environments, we don't create artifacts that adversely affect your computations or your analytics for the voice of interest on the back end. And at a high level, yobe unlocks the potential of voice technology by allowing the maximum amount of data to be extracted from your voice signal. Again, my name is Ken Sutton. Here's our contact information. And please feel free to reach out or go to our website and take a look at some of our demos. And hopefully we'll be looking forward to talking to you soon.